Okay, so let's continue. Right, so the first thing I want to do today is talk about what happens if you just have baryons in the early universe. Okay, so last time we did the case of pure dark matter. We should really include both, but now let's sort of switch to imagine hypothetically pure baryons. We can more or less solve that, and then we can comment on what happens when you put in both. All right. So our universe now is baryons. And these baryons in the early universe are tightly coupled. They're charged in the early universe, right? It's ionized plasma until about 380,000 years. And so we definitely have to worry about their coupling to the photons. So it's going to be some baryons and photon fluid, which we wish to discuss for a few minutes. And we're going to ignore dark matter. Okay, so this is not realistic, but it's also a conceptually important thing to think about. So our equation, right? And so first of all, I'm going to define for you, I'm going to write delta now. We're going to write, I don't know, delta sub B gamma, because it's a combined fluid when they're coupled to each other. They're tightly coupled in the early universe. Is that fair? So our equation now is this delta double dot. And then we have to track the sound speed. That's going to be super important for us. Okay, so that's our basic equation, the density perturbation at linear order. And I've just rewritten it, and I just put some B gamma subscripts on everything to remind us that's what we're now studying. Okay. So this sound speed is precisely the thing that we said was negligible for dark matter, but now we need to track it. So the sound speed is, remember, the derivative of the pressure on the background with respect to the density of this baryon photon coupled system. Okay, so imagine a single fluid. So we have to just take this derivative of the pressure of the system with respect to its density. So let's write out what the pressure is. The pressure is basically the pressure of the photons, right? Well, it's the pressure of both. Okay. But, you know, it's photons that carry a lot of pressure. Their pressure is 1/3 their density. And the pressure of baryons is tiny. Right? It's a non-relativistic system. So this is very good. We're used to saying in this course, matter has negligible pressure. And then on the other hand, the density, well, all I can do is say it's the sum of the two things. Okay. And so in the early universe, the photons dominate, and as you go on, the baryons start to become more and more important. Right? The crossover is no longer 47,000 years. That's when the total matter balances the photon density, equality. This is just the baryons. So, you know, in some sense, that would be later. But we don't have dark matter, so it depends on your point of view. Okay, but is everyone all right with this? Okay, so to get the sound speed, we should somehow be differentiating this thing with respect to that thing. So that requires a little bit of thinking. Let's just start with the early universe, where rho baryon is much less than rho photon. Okay, so in that very early universe, you could just ignore even the density of the baryons. So this is super easy. You're just differentiating 1/3 rho with respect to rho. Fair enough? So our usual statement that the equation of state for photons, for radiation, is 1/3. It's also manifesting itself in the sound speed, or the sound speed squared is also 1/3. Okay, so CS of this combined fluid is then 1/3. And then I can leave it as maybe an exercise. It's very easy to incorporate this other term to be a bit more general. And one can check that the sound speed, when you include both, you have to do just a little bit of thinking as to how to take the derivative. Looks like this. Okay, so far that's a funny way of writing the number a third. There's just this factor that's 1, but I have a correction which ends up being 3 rho baryon. Okay, this is the more general result. Okay, maybe I'll put this exercise on the homework or something. But is that okay? You'd have to figure out how to take the derivative of that with respect to that funny thing. And that looks a bit weird. How do you differentiate one variable rho gamma with respect to rho gamma plus another variable rho b? And what you can do is just note how they both depend on the scale factor. This is 1 over a to the 4. This is 1 over a to the 4. This is 1 over a cubed. So you can use the chain rule to figure out how to differentiate everything with respect to the scale factor. And you can readily derive this. So in any case, if we plot this thing, let's plot CS squared versus, well, let's say time. It's basically starting its life at a third. Okay, you're in the radiation era where you could ignore rho baryon. And then as the baryon density starts to become more and more important, as we head towards the matter era, it will go down. Okay, so this is already, I don't know, depends on the baryon density. This is already a few hundred thousand years. Is that okay? I don't want to say 47,000. You get my point? We have to wait even longer because it's only the baryons. And then there's a point at which we don't trust any of this. So when we're beyond 380,000, what should I do beyond 380,000? Should I trust any of this stuff? What happens beyond 380,000 years in the conventional cosmology? Yeah. We got recombination. Yeah. So beyond 380,000, the photons have decoupled. So beyond 380,000, these kind of formulas don't make sense. This is imagining a tightly coupled photon baryon fluid, a single fluid where you perturb photons and the baryons perturb with it, the single material, if you will. And at some point, that approximation is getting worse and worse. And you should just, eventually at 380,000 years, you have another simple thing, which is just to talk about the baryons. And they don't know about the photons anymore. They're just passing by them. They're ignoring them, just like the neutrinos are passing straight by. Okay, so there would be nothing to provide this pressure beyond about 380,000. And so this thing here, let's be concrete, let's say 380,000. This somehow should absolutely plummet. Does that make sense? The effective sound speed for the baryons is going to drop like crazy. All right. So this is after recombination, or if you like, photon decoupling. All right, in the early universe, however, the sound speed is basically a third. Well, the sound speed squared is a third. Okay. So CS is basically 1 over root 3 early, or about 0.57. Remember, this is all in units of the speed of light. If I put C back in, okay. So early times is coupling to photons means that the typical speed at which perturbations move at, the figure of merit is the speed of light. Okay, even though there are many baryons themselves are non-relativistic. Okay, so if you have a little, over density or something or other in your material, this thing is going to move out at this 0.57 C early on. Okay, so this tight coupling to photons, remember there's a gazillion photons around, there's a billion more photons than baryons. It means that you perturb your system and then 0.57 C. Okay, it is a fluid, so we cannot, then it's not trivially just that everything's moving out at C. These photons are banging into the baryons, they're coupled to it. So we should not imagine that the speed is literally C, but C is the figure of merit, and it ends up being this 1 over root 3C. Is that okay? Any questions about this? Yeah. That is all true as well, yeah. So basically, these perturbations here, as we're about to discuss, will oscillate. Okay, there are oscillations, frequency, and they're related to the indeed the oscillations in the same. That's right. We had a lot more time in this course. We could get into that in detail, but thanks for mentioning that. Okay. So relatedly, I want to now double check, since we have a formula for CS, let's say in the early universe of 1 over root 3, we want to go back to this equation here and see under what condition we can either oscillate, right? That's for K bigger than K genes, where this is positive, or we have gravitational growth of gravitational growth, where this thing is negative. Since we have a formula for CS, we can check when that is true. Okay. So let's identify the genes scale. I just set that thing in brackets to 0. That's CS squared. K genes for the A squared is 4 pi G rho baryon gamma. And as we did last time, this 4 pi G rho, we can rewrite it in terms of like 3/2 H squared. Remember that little trick? So this is actually 3/2 H squared. And well, I guess it's only the baryons and the photons, so I guess I should include an omega baryon photon. Okay, that's the fraction of that component. So if we ignore dark matter, the universe is almost all baryons and photons anyway. So I could probably just replace omega by 1. And okay, technically there are neutrinos around, so omega is not quite 1, but it's near enough. Is that okay? Omega is more or less 1, or a little bit less. That's not going to affect our thinking too much. Okay, so that means that the physical wave number, Kpj, which is Kj over A, the actual honest to goodness physical wave number from solving this thing is then, I don't know, root 3 over 2, root omega H over CS. And if in the early universe I put in CS as 1 over root 3, you can see this is going to become root 3 here. Did I do that right? Tell me if I make a mistake on the board. Is that right? Let's say CS is 1 over root 3. Okay, the corresponding wavelength, lambda physical genes, which is just 2 pi over K. I just invert this whole thing. Okay. Root 2/3, 1 over root 3. This number's not going to matter for us much. And there's a 2 pi. And then there's a 1 over H. Okay. Reinstate factors of C for a moment. This is C over H. There's a funny number sitting out front. Okay, omega baryon gamma is about 1 or slightly less than 1. And then there's some 2 pi's and so on. So I think you can see this prefactor here is a little bit bigger than 1, thanks to the 2 pi. And C over H, remember that's our friend, what's that? What length scale what's that thing? That's the Hubble length, yep. So this thing here is the Hubble length, DH. So you see this thing is slightly bigger than Hubble length. Okay. So for lambda greater than lambda PJ, remember, this is gravitational instability, and it's lambda less than, we have oscillations. Okay. acoustic oscillations. But what we found is something interesting, which is to have the gravitational instability, we have to go to insanely big wavelengths. Namely, they have to be bigger than the Hubble length itself. These are gigantic wavelengths. According to these calculations, according to this formula, those are the modes that could grow with a gravitational instability. And on the other hand, every wavelength that's less than the Hubble length is going to oscillate. They're not going to grow. Now, I have to say something now, is that this conclusion here is actually wrong, because this is bigger, right? So this is bigger than DH. And when you consider modes that are that big, you might remember our derivation of these formulas was essentially Newtonian. We did Newtonian gravity. When you're dealing with lengths that are that large, right, which are controlled by C, it's bigger than DH, you need a general relativistic analysis. Okay? So we can touch on this in the next couple of lectures, but the punchline is that irrespective of pressure and so on, modes that are bigger than the Hubble length are actually frozen. They don't evolve at all. One word as to why that's true is it would be causality. When they're that big, somehow there's not time for this part of the overdensity and that part of the overdensity to communicate with one another and know that they need to attract and grow. But in any case, we are revealed these modes are frozen. They don't talk. Okay, so our real punchline, which is true for dark matter as well, for anything. So our real punchline is that every mode that's less than the Hubble length, and you can try to get away with the Newtonian analysis, they just oscillate. Totally different than dark matter. So this is the main thing we've learned in our where the Newtonian analysis is valid. Any questions about this? All right. So let's now consider the growth over time, because eventually we're not going to have this problem, because eventually CS is going to go to 0, right? So the pressure term will disappear, and then it will be analogous to dark matter. This has gravitation. Fair enough? All right. So if I do a plot like we did last time, we try to plot it to be time, and this was a density perturbation. And I gave you as an example, I said, well, maybe it starts at 10 to the minus 4 delta, 10 to the minus 4, let's say. And we said, oh, let's lay that down at 1 second. That was our random example. Let's do that again. So when the universe is 1 second, we're at 10 to the minus 4. And up here, I'm going to label 380,000 years. Because earlier than 380,000, we have this big pressure, this big sound speed to worry about. And this has meant that we don't get any growth for these sub-Hubble scales. So this curve here is basically, it's just oscillations. That means the amplitude is not growing. That's more or less just a flat line. Does that make sense? Oscillations, that's the amplitude, no growth. Yeah. Oh yeah, so I'm plotting for you delta of the baryons, which at this stage I could write delta B gamma, but eventually I just call it delta B. Now, after 380,000 years, the CS is plummeted. So it's all gravity. And we are in the matter era. So what did we learn from last time? What should be the growth here? Matter era, just gravity. Linear. Yeah, linear in the scale factor, right? Or t to the 2/3. Yeah. So it's some power law here, okay, like this. And then at about 10 gigayears, we become dark energy dominated and it kind of flatlines, and that is about today. Okay. And this here is at a redshift of about 1100. Okay. So since this is linear growth in this regime, linear with a scale factor, from here to here, remember this is let's write scale factor. A is 1 over 1100, and here this is A of like 0.75. My growth, go down a little bit. My growth is linear in the scale factor. So I just pick up the ratio of these two numbers. Does that make sense? It's linear in A. So the value here, delta, is going to be something like its initial value, 10 to the minus 4, times 1100 times 0.75. Okay, linear in the scale factor. And so this is about a factor of 1,000, so this is about 0.1. Oh. So the whole history of the universe then, the delta baryon grows in the matter era, maybe picks up a factor of 1,000, you're at 0.1. 0.1, first of all, you still can more or less trust the linear theory. It's not so big. And these modes are still going to be dragged with the expansion of the universe. They're still just going to expand. At delta of 0.1, you should not expect significant gravitational collapse into structures like galaxies, clusters of galaxies, and so on. Make sense? This is too small. We need delta to be about 1 or bigger than 1. So this is a boring universe. This is essentially a universe without galaxies. So that's a big deal. Okay, now let's put on top of this thing our dark matter from last time. So dark matter, we also started at 10 to the minus 4. And then I should mark somewhere here. I should mark somewhere here the matter radiation equality, 47,000 years. That's a redshift of 1 over 3,600. That's important because we had log growth in the radiation era. Right, so there was some log curve we discussed last time. And then we enter the matter era, and it was then linear, just as this. So these curves here are kind of similar shape, and a bit of a flat lining when you enter the dark energy era. Okay, and we got from here to here. This was about a factor of 15 if we, from our estimates last time. We picked up a 15 from the log. And then you have to redshift from 3,600, 0.75, around about another factor of 3,000 or so. And then the final value here, delta D, we remember was about 4 from last time. Okay. So somewhere around about here, let's say this is delta of 1, where things are really nonlinear and you can have gravitational collapse, galaxies and so on. Okay, so these two curves is pure dark matter universe, pure baryonic universe. We have not put in both. I just drew them on the same plot. Any questions about this? All right. So, yeah, so let's highlight this one. Let's just say, so therefore, no galaxies. That's a little sad. Okay. So now we can think about what happens if we include both, right? And we want to bear in mind that, 85% in the standard model is the dark matter and about 15% of the baryons. Okay. So if you put in both, you can imagine that the dark matter curve is not going to change very much, right? It might change at the 15% level because it's talking to the baryons gravitationally. Okay, so I'm not even going to bother to redraw the red curve. Is that okay? Now that I include both. 15% correction. On the other hand, from the baryons, that's going to radically change its thing because now there's this 5 times extra stuff out there that I forgot to include in this analysis to get this curve, right? And so the pressure in early times is still so significant that this thing is going to struggle to grow. But the moment the pressure is switched off, right, the gravitational coupling between the baryons and the dark matter is so significant that you can imagine the baryons are going to want to fall towards where the dark matter overdensities are. Okay, so if you're here, so let's put in blue the case of including both. So I claim it should be something like this. It's not going to be too different. And then we get here somewhere. So we can look at an equation in 1 second. But if you have a big, you look here, right? This delta just means there's a relatively big dark matter density perturbation. It's not that big, it's not 4, but it's say, I don't know, 0.1 or 0.5 or something. And then the baryons say, oh my goodness, there's a big overdensity there, let's fall in gravitationally. So their density is going to start to grow. Their overdensities, and their underdensities will get more underdense. So you can imagine a curve that will look something like this. And I claim it will actually track the other solution at late times, and they'll look very similar. Okay, so this is when you have both. And I'm more or less claiming that this is both, even though technically I should draw a slightly different red dash curve, but that's not going to look different, too much different. So let's look at an equation as to why I claim that they will actually track each other. Physically, as I said, right, it's just gravity is attractive, so they should fall where one is overdense, the other should be overdense. But we can see it mathematically. All right, so let's write down the dark matter equation. That's just delta D is sound speed negligible. And then there's going to be minus 4 pi G, right? And I should write rho bar delta. But there's the contribution from the dark matter. And there's the contribution from the baryons. Right? This is the gravitational term, and everything sources the gravitational potential. So I have to write down both density contributions. Does that make sense? They both source phi Newton. And then the equation for the baryons, let's say after decoupling, photon decoupling, that means I'm not going to bother with CS. We're going to set CS to 0 because I'm saying I'm only interested in the equations in this era. It's going to look almost identical, but I have a B subscript. In fact, it is identical other than the B subscript. And they're going to have the same source of gravity. Is that okay? So now they're just, two gases. It's a red gas and a blue gas. And if neither of them feel pressure and they both feel gravity, they're going to evolve under the same equation. Now, these are differential equations, right? They have infinitely many solutions. There is one, let's say, special solution which we can look at, which would be delta B equals delta D. Fair enough. You set delta B equal to delta D, the two equations collapse to the same equation. So this has to be one of the infinitely many solutions of these equations. Okay. Now I claim that this thing is actually an attractor solution. Okay. It's not the solution because if you start here, they have different initial conditions. So that can't be the right solution, but it's actually an attractor. They head towards each other. I claim delta B is an attractor. And perhaps you can prove this on upcoming homework. Okay. So that just means that you just set, if you set the two equal to each other, but then you allow one to be a little different than the other, you'll find that over time they like to go back towards each other. That's what an attractor means, right? So anyway, it does this. Questions about this? All right, so the baryons, thank goodness for the dark matter, they can end up forming where the dark matter can provide the seeds for the gravity for galaxies, and the baryons are kind of falling into that as well. Yeah, sure.
About how like large galaxies form larger than expected compared to dark matter model. If that is sensitive to the initial conditions in the dark matter model, like can you adjust the initial
Right.
conditions to account for bigger size galaxies for well?
Do you also mean like early galaxies, like from JWST?
Something like that. It's sort of like bigger than expected.
Yeah, I think bigger than expected, especially at early times. Yeah, I don't think I'm, yeah, I guess we can imagine that these are flukes in the tail of the distribution. But I think what I'm presenting here is the sort of vanilla lambda CDM version, which there is perhaps a bit of tension with that. But I think quantifying that tension is a very messy business. So we don't know to what extent we should really worry about that. But it's certainly an active area of research. Because, for example, there's all sorts of selection effects. We're very good at looking at the big galaxies. We're not so good at finding the smaller galaxies. So whether it's a selection effect, we don't know. But that's a really good question. So I'm not going to, so there's a chance that there's something really big going on there. Okay. So broadly speaking, things work well. These way of understanding things works well, but at the edges, we're not totally certain. Okay. So I want to talk a bit more now about the statistics of these fluctuations. Now you mentioned these points in some sense. I want to quantify these statistics. Okay. So I've been writing here these deltas. Okay. And we can mainly, because they attract one another, from more or less just talk about a single delta. At this time, they're basically the same. So, and I've given you as this sort of fiducial value 10 to the minus 4. Okay. What are these things that we're talking about here, right? This is some messy field. It doesn't have a single delta, right? If I plot rho versus position, there's some mean that we called rho bar. And then there's all sorts of fluctuations around it, right? Crazy stuff. And this gap here we're calling delta. Okay, the percentage gap, right? Rho is rho bar brackets 1 plus delta of x and t. Okay, so I cannot say to you at initial time or at any time, the value is 10 to the minus 4. It's a whole messy thing. I could, for example, and what we'll often focus on is trying to make a statement about the amplitude of a given Fourier mode with wave number k. That would be a particular number, which we could specify, but have to specify one for every mode. And in a suitably normalized sense, that thing is on the order of 10 to the minus 4 initially. But even that is not guaranteed to be 10 to the minus 4. For example, a Fourier mode doesn't have to be even real. So Fourier transform can be complex. It could be positive, could be negative, can be complex. But if you take the magnitude of it, I claim order of magnitude is on the 10 to the minus 4 level. So let's maybe, yeah, perhaps we can look at a movie and get a better idea. Hopefully. Okay. Let me just remind you of this. I'm going to show you a different movie in 1 second, but just again, a recap from last time. We talked about this movie, which is in a relatively small box. Okay, so if I evolve this thing to the end of the simulation, again, we have to talk about structure on different scales. And the final image of this thing, first of all, this box is not really big enough to make really clear what's going on. If this was our whole universe, let's say, it would be a bit funny because I guess you could say there's a giant patch here in the universe that looks like its density is significantly less than that patch. If this was the whole universe, that'd be very big inhomogeneities on large scales. So this is really just a small patch, okay? So let's look at another movie. But the next movie is only going to be at this time, which is today. We're just going to take an image of today. And all the movie will do will be to zoom around in different places. Now, you may have seen this movie before. Where is it? Okay, so this is Millennium Simulation. And again, this is having evolved the equations to today. So this is the output today. And you can think of this as a big chunk of the universe. So you see the scale there is a gigaparsec. Okay, so a few gigaparsecs is a whole observable universe. So this is basically the whole observable universe. Okay, because remember, parsec is about 3 light years. So that's like 3 billion light years. So this is roughly, like order 15 billion light years, our Hubble length. So that's today. And so you see by just staring at it today, it's looking pretty homogeneous on large scales. Okay. So the statement that the universe today is homogeneous on large scales, this is a simulation. We have to compare this to data. But if we accept for a moment that this is consistent with the data, you can see visually that we are talking, even today, homogeneity on large scales. But we are not talking about homogeneity on small scales. So then we can zoom in. Okay, because I promised you that for certain modes, at least, they can grow to have delta. Right? On a large scale, it might be 10 to the minus 4, but as we go to smaller scales, those deltas, I promise you, could get big. For example, delta of 4 or something I was estimating today. And this is consistent with the fact that those big inhomogeneities are seen on smaller wavelengths or smaller scales. Okay, we have to get into small scales to see that. And of course, it's the small scales where we start to see galaxies, clusters of galaxies, and so on. So those are the scales which eventually, after a long, long, long evolution, have a big delta, but not the wavelengths that are super big. The wavelengths that are super big, for reasons we can discuss, have never had time to grow very much. It's related to a point I made over there. All right. Okay, so this is yeah. Hopefully that gives you an idea. So questions about this? Okay, so a bit of effort we have to understand. On the larger scales, we still have very good homogeneity at 1 part in 10 to the 4, roughly. I'll quantify it soon. On smaller scales, much bigger inhomogeneity. And it all arises, essentially, from the equations we've been solving, this evolution. Okay, so there's not, the nonlinear stuff, we have to go beyond what we've done. But to have a good understanding of this, qualitative understanding of this, is these kind of linear equations that we've been studying. All right. So now I want to talk about the statistics of these inhomogeneities. Okay, here we are. So I would like to say something about like the mean and the variance, things like that. So let's think about delta. Again, we're after recombination for the point of this exercise. So we're just going to talk about delta. I'm not going to distinguish delta B and delta dark matter. Is that okay? You can think of it as essentially the dark matter if you like. So this thing has a mean. And I hasten to ask, what is its value, given I know the answer is coming. But perhaps we can see on the board here from this equation, the mean of the delta has to be 0, right? Because by definition, we factorize the mean, which is rho bar, the homogeneous background. So the mean of our perturbations, delta, is 0. So that doesn't tell us anything much. Okay? So again, it fluctuates around 0. So we're going to focus a lot, therefore, on somehow the variance of delta. So we can look at delta squared. And let's remember this delta can be a function of position and time. And I want to take somehow I'll talk about the average of delta squared would be the variance. Okay, now, if let's say this is our universe at some moment in time, looks like that, rho versus position. If you take a particular x, like let's say you take this value for x, you could say, well, the rho is just that number. So the delta is, 0.1, let's say. So what's the point of taking an average? The number is just 0.1. What does that mean? Okay, that sounds a bit silly. But on the other hand, you might, if someone says, well, what's the average or the average of delta squared? You might say, well, what I mean by that is somehow averaging over space. Okay, so we could define this by a spatial or volume average. As, let's pick a region of the universe. You plonk down X somewhere. And yeah, sorry, let's say this is X. And then there's some, messy universe with all of its inhomogeneities that I can't really draw. And then you average over this region. Let's say this region has volume V. So we could write it as the integral over V, some dummy variable Z that takes me to some other point. So this is some vector Z to some random point. And then I take the thing inside the expectation value, delta of X plus Z, at some moment in time t, and I square it. And then we normalize. Does that look like a volume average? Pick X, and then you average over some volume surrounding it. Now, if the integration volume is the whole universe, then okay, you just got some number. It doesn't really matter about X, because you integrated over everything. But you could imagine integrating over a sub piece of the universe. So let's say there's another region here. And you could imagine repeating the exercise over this region. I could then do it for this X, and then I can come along and do it for this X, and integrate over that volume, and so on. Okay? So you could imagine that the variance here and the variance there could be different. You integrate over different regions. Okay? But the statement of statistical translation invariance is the statement that this number is basically the same, doesn't really depend on X actually. Doesn't matter if you average over this region or you average over this region. Okay? As long as because you have to average over a big region. If you integrate over a tiny region, it's not going to work. If you pick X to be the center of the galaxy and your volume is just the galaxy, and then you pick X to be a gap between galaxies, integrate over that, you're going to get a totally different answer. But if you pick a sufficiently big region that houses many, many galaxies and so on, let's say gigaparsec, for example, in the movie, this averages look to be basically the same. So basically delta squared is independent of X. Okay, so we could just call it delta squared. We don't even need to specify x really. But we can remember that it depends on time. So that's the variance. But there's something more interesting we can talk about, right? Where we don't just throw away spatial structure. Well, let me actually make another comment. So our data indicates that the statistics are Gaussian. As far as we tell, the fluctuations, or at least the primordial fluctuations, look to be Gaussian. And it's a very big deal to be sure that that's true. So far, we have not seen any deviations from Gaussianity in the statistics of this thing. Okay, so what do we know if it's Gaussian? Yeah. Right.
Systems are physically interesting longer than.
Yeah. No, it will be okay. There are these big modes as well, but you know, it's okay if you're interested in a very big mode, whether they're frozen or not. To even talk about the statistics, first you'd have to put that in some volume that houses it, so a big volume. But the statement would just be that the variance, if you like, the sample variance over that big volume is still the same as a sample variance over some other big volume, right? So we may be at the center. We may be at the center of one of these, okay, because that's our observable universe, because you're talking about such giant modes. But we could imagine that there's some other region out there. So our universe, remember, could be infinite in spatial extent. So whatever mode you're interested in, even some whopping big mode, you could imagine there's a volume bigger than that that allows you to compute this average. And then you could imagine in your mind repeating that in some other region, and you'll get the same answer. For those modes that are so big, we don't know that that's guaranteed to be true. So I say data tells us that is not guaranteed anymore for those huge modes, but we could imagine it is. Does that answer it? Okay. Oh, okay, good. So Gaussian, so, you know, if you have any statistical variable, right, Gaussian literally means that that the delta is drawn from a Gaussian. Okay, so what I mean by this is that the probability distribution for delta, let's say at a given point in space, I want to go beyond this in 1 minute, but the probability distribution is proportional to exponential minus delta squared over 2, I guess I call it sigma, I don't know, sigma squared. Deltas versus sigmas. Okay. Sigma here, the standard deviation. So that sigma is going to be related to our 10 to the minus 4 typical value that I've been suggesting to you. But I'm going to have to be more precise than this formula in a minute. But is everyone okay? So at a given point in space, let's say, as far as the statistics are concerned, the number that we see there is just some random value for the density fluctuation, as though it came from a Gaussian with some standard deviation. That's what I mean by Gaussian. And so, you know, statistically, of course, I mean, mathematically, this makes things super simple because our mean is 0, because the way we've defined delta. We'll have a variance that we're going to have to spend a long time discussing with a little more detail than this. And then we just truncate it, because when a Gaussian is completely specified by its mean and variance. So I don't have to go, you know, you could imagine, and people do check, right? So the business of saying the data indicates things are Gaussian means that people have checked about other moments of the distribution. So you could check on like the 3-point, delta cubed. And the data indicates that this is 0. which is what a property of a Gaussian. And you could check on having 4 copies of delta, right? Delta, well, yeah, 4 deltas, or delta to the 4. There's a reason I separate them, which I'm coming to in a minute. And for a Gaussian, if you have this, it's related to the variance. I think it's like 3 times the variance or something squared. Okay, but anyway, you can get any other moment you want from just the variance. So anyway, people, yeah, so the data tells us that this looks like 0, and the data tells us that this thing looks like that, which is a way of checking that it's Gaussian. Yeah.
This gets a little funky when delta gets 1.
Oh, that's a good question. Yeah, that's right. Technically, this is all at sufficiently early times that delta hasn't got towards 1. That's right. The nonlinearities force this thing. So in full disclosure, that millennial simulation we saw, the statistics of that are not Gaussian when you enter the nonlinear regime. But we have been very good at trying to map out the early statistics, what things look like at early times. And those things look to be Gaussian, so primordial. Okay, now the thing where we have to talk more about is that even at the level of the variance, okay, or this sigma here, there's actually some more information a Gaussian can have than just this, because this is just one number. And for example, you know, there cannot be enough that I can't possibly tell you everything with one number, sigma, because this delta is just not a single number. It's a function of position, right? So how am I going to tell you that it looks, you know, like this thing? Okay, even the statistics of that. So can anyone think of something a bit more general than this? There's something more, is there a quantity I could consider that's a little more information than just that thing? At the level of 2 copies of delta. The delta, what else could I do? You may have met it in some other course. Okay, so this, yeah. Uh, well, we don't really know about temperature at this stage. This is just, yeah. Well, okay, maybe the temperature is in the space of theories concepts where we sometimes think about correlation lengths in a system and how temperature impacts that. So yeah, we may be interested in something like a correlation length, right? So if I have a perturbations that look like this, and I tell you at a random point it has a variance, say 0.1, that's one thing to know. But this, if all I tell you is sigma, okay, so let's just draw delta for a moment with the understanding we've subtracted out the background. So this is delta versus position. Okay, let's say that sigma is 0.1. I don't know, it doesn't matter. Here's 0.1, here's minus 0.1. Now I plot delta versus position. You could imagine something that would be compatible with this is that delta versus position is something that goes like this. Okay, it looks like the standard deviation is about 0.1. But you could also imagine that another thing that could happen is that it looks like this. Right? So that the variance may still be, or the standard deviation might be 0.1, but in the red curve, it's a lot longer, it's not much longer wavelengths. So there's a bigger correlation, you would say, in the red curve than the blue. Okay, the moment you walk over there, in the blue, it basically forgot that you were at positive and it jumped to negative. There's very little correlation in the blue. You could even imagine an extreme situation where these were just random dots jumping up and down like crazy. One doesn't care about the other. But the red is telling you that they're correlated. Okay, so there is a correlation length, you could say, potentially. But the more general concept is a correlation function. So I write this as delta, yeah, I can write delta of x, and then I can consider another point in space, which we could call y. So at a given moment in time, that's actually the most general statistic I can refer to for a Gaussian, is that two-point correlation function, as it's called. 2-point, which is two deltas. So indeed here you could imagine delta of x, delta of y, delta of z, and go to town with different positions in space. That's the more general idea. So that's a lot more work to check on those things. And we can give this thing a name. I can call this often xc of x comma y. And I guess it depends on time. Okay, so if you have 2 points in space, now here's x and here's y, you just literally compute the fluctuation here times the fluctuation there, and then do an averaging on that to figure out what this thing is. And that will, yeah, tell you whether there's correlations over space. And if I set x equal to y, this just collapses to the variance, right? So the variance, which we guess we could call sigma squared, is xc of xx. All right. Okay, so now this statement of translation variance has some content to it. So translation variance tells me what about xc? Let's say we have statistical translation variance. Right? Remember here it said that the variance is independent of x. So if I have a function, this correlation function, what happens at x versus y, what would translation variance mean? What does statistical translation variance mean? Right, so remember, basically means you do statistics in one volume and you repeat it in another volume, you get the same answer. So what would that mean mathematically? What could you say about xc? What is it a function of, really? Just one of the vectors? Okay, well then what do you do with the other vector? Okay, you could set it to 0. That's a way of putting it. That's true. xc, you could do that. Or we could, yeah, you could take their difference is another way of doing it. So xc is really just a function of x minus y. Okay, translation variance means you have a vector here, x and y, and you run the statistics of how they're correlated, and then you repeat the experiment over here, you have to get the same answer. That would be statistical translation invariance. Okay, so it's not really a function of these 6 coordinates, x, y, z there and the x, y, z there. It's a function only of the difference. Right? So again, here's x and here's y. And you repeat it for, I don't know, x prime and y prime. And as long as this vector and that vector are the same vectors, you get the same answer. And then there's one more thing, which is rotation invariance. Okay. So this means we take our distance, our vector between x minus y, here's x and here's y. If we have rotation invariance, it means I can get the same answer if I rotate those vectors. So then it's only a function of literally the distance between them. So xc is just a function of, let's say, r comma t, where r is just the distance, x minus y. Okay, so this thing is not too bad. We were worried it was a function of 6 coordinates, but really it should only be a function of 1 coordinate, literally the distance between the 2 points in space. Okay, so that means if there's another pair of points, I don't know, let's say x double prime and y double prime, as long as I didn't draw it very well, but as long as this distance here is r, this distance is r, and that is r, They all have the same correlation between them. Yeah. Just tell me how far away these 2 points are. That's all you need to know. Okay, so if you, well, in one dimension, these things are a lot easier to imagine, right? The translation invariance, like if you had some spin system, so let's say you have a chain of spins, some are up and some are down. And this is just telling me, if you tell this, if you say, for example, you tell me this spin is up, you want to know, well, tells you something about like, what are the odds that the next one is up, and the one after that, and the one after that, and the one after that. So maybe this has a 90% chance of being up because they're coupled to each other. Maybe the next one is an 80% chance and the 70% chance and so on as the spins get further away from one another. But if you ask me, okay, what about if I take this one over here up? Well, you imagine it's still 90%, 80%, 70% because you imagine that the physics of the chain here is the same physics as the chain over there. Okay. And then a higher dimensional chain, you can talk about rotating it and so on. All right. Yeah.
So with the whole taking an average thing, that seems like it'll be sensitive to the size of the region that you're taking an average on. So how big a region are we talking about? You're going to be the same as before on the scale of the.
Well, yeah, so I mean, ideally, yeah, you take a region here that's, okay, so this translation variance to have content, you have to imagine you take a region that's somehow big compared to R, otherwise you've got no chance of getting the statistics right. And then you can compare another pair that are somehow outside that volume as well. So it's a bit of a statistical, it's an issue to get all these things precise. Right? You can talk about the statistical variance and so on and so forth. But parametrically, yes, if this is X and Y over here, I take a box that's big compared to R, and then I imagine another box big compared to R over here. Yeah.
Because you've chosen a favorite framework. And now, if I imagine I'm an observer and I'm traveling along the direction that you've drawn with the point X to Y, I'm trying to boost along that frame. I've now contracted that arc, but I haven't contracted the arc that goes X prime prime, Y prime. Which seems to have broken the rotation there. But the new boosted frame is just a good frame.
Okay, but I have in mind all these things are that they are in fact all at the same time t, or let's say us. We're the observer and we're in this frame. And I can imagine there's all these density perturbations in our universe according to us at our t equals 13.8 billion years. And I just want to compare the statistics of that arrangement of the millennium simulation, let's say, or the real world actually, but just millennium, something to point to, of how the correlations are in that point on our millennium simulation versus that point. So the things would be, what you're kind of asking about is, things can get tricky if you then boost to someone in some other frame and ask to compare our statistics with them. And in fact, the answer to that would be that depending on the frame, most frames in the universe in a way will not see rotation invariance in a sense, because there is a preferred frame. It's the frame where we're at rest with respect to the expansion, which is a frame that we are almost in, but we are not quite in that frame actually. We do have to boost a little bit to get into that frame. Right? So as we orbit the sun, for example, we cannot stay in that one sacred frame. And even our solar system is not in that frame. But once you get into that frame, then you just run the statistics. You just ignore relativity in a sense. Does that make sense? Because we're talking about rotations, and I'm not putting a statement about boosts on the board. Yeah. Other questions? Yeah. If we wanted to be fancy, I guess we could. Well, okay. So related to that, there is, and in some ways related to your question as well, we could go further and worry about this thing at two different moments in time. So this would be the most general thing we could talk about actually at the level of the 2-point correlation function. Okay. So we could worry about things correlated in time as well as space. But for my discussion, equal time will suffice. But yeah, maybe T and T prime could be closer to a propagator. Okay. So, okay, so sometimes we talk about this as I've presented it so far, just in position space, but it's often even more powerful to talk about this stuff in K space. But I hope we're happy with this, so that at least at a given moment in time, the complete specification of the statistics of a density field that's Gaussian is entirely encoded in this one function. This is just a thing. If you set r to 0, that's the variance. But for non-zero r, it's a more general function. And if it's Gaussian, there's nothing beyond the 2-point anyway. So we just need the correlation function and we're done. Okay, then we might like to move to K space. And that would mean I write integral d3x. I just Fourier transform this xc. Okay, I mean, I can sometimes, well, I guess I can write comma t. It's always understood these things are time dependent as the universe expands. And the Fourier transform, I know I've often written xc hat, okay, as my name for a Fourier transform. But in this business, almost no one calls it xc hat. They call it capital P. Okay, not probability, but capital P. There's a function of k, and that's called the power or power spectrum. Okay, spectrum reminds you it depends on wave number or wavelength. Okay, so equally well, since this is a function of one variable, rest assured its Fourier transform will also be a function of one variable, and I guess I should write comma t. At some point, I'm going to drop writing the comma t's all the time. Is that okay? There's rotation symmetry here, so you don't really even need to do the 3D integral. I guess I could write an r there. Yeah, the angular integral is trivial. So this is really just a one-dimensional integral. And then the inverse Fourier theorem just tells us, of course, we can reconstruct xc from the power. Okay. So we can go either way. Often in this business, people like specifying the statistics by specifying the power spectrum P of k, with the understanding that it's just a Fourier transform that can give you back your correlation function in position space. Okay, let me also, I don't have time to derive this, but maybe I welcome you to try this as an exercise. You can ask, right? So this is the 2-point correlation function in position space. You can equally well ask, what is the 2-point correlation function in K space? It should be related to P. And the relationship, I'll just write as an exercise. If you ask what is, say, delta of some K, and delta, nice to write delta conjugate of, say, some other K, K prime, okay? 2 different K values, right? That's the K space analog of that thing, X, Y, K, K prime, or whatever you want to call it. And, well, anyway, the conjugate is just convenience. And you can check that this is, in my conventions, 2 pi cubed, 3D delta function, K minus K prime, and then our friend, the power spectrum. Okay, so in position space, the 2-point is literally xc, but in K space, the 2-point is P, it's Fourier transform, but there's a delta function prefactor. So this thing only hits when K is K prime. When you have translation invariance, two different K modes are completely uncorrelated. It's like we can write delta K K prime, right, is, let's say 0, for K not equal to K prime. And if you put things when K equals K prime, it looks a little disturbing because then you hit the delta function. But you can imagine putting this thing in a big box. When that happens, your K modes become discrete. And if you define it in a big box, this delta of 0, it just picks up the volume of that box when K equals K prime. Oh, and I need to multiply by the P. Okay, so up to some volume factor, some annoying thing that you often have to drag around when you take Fourier transforms. Yeah, morally, the 2-point function is this. Okay, and sorry? Now, imagine you're just living in K-space, and V is just some big volume. Yeah, so whatever the box size that you're studying is, that's the V. Is that okay? So this gets into some murky territory because I live in K-space. Okay, but think of this as just the usual sense in which you have an average. Is that okay? So yeah, that's a slightly tricky thing. I have to tell you about the ergodic theorem and all sorts of stuff. Think of it as averaging over the volume, if you like, as a short answer. No, but what is that? That doesn't mean I can't write the letter V. There is a volume. So is there a contradiction?
Well, I was just wondering if that was before or after.
No, well, okay. You take the way I've set up I mean, some people, that's kind of getting back to the definition of Fourier transform. Some people could define a Fourier transform with some 1 over root V here and so on and make that cancel out. I'm not doing it like that. So this thing is not too deep. Let's put it that way. All right. And so you see when K is K prime, right? For K equals K prime, just to be clear, this thing is just delta of K modular squared. So it's the variance. All right. Okay, good. So to start of next time, we can talk about what the primordial power spectrum looks to be in our universe. And then we have to talk about ideas as to how we got there in the first place. So that would be related to inflation. All right, thank you.